With 50 million sales, it was the best-selling album of the 70s, and it's the third best-selling album of all time. Its simple yet thought-provoking cover art and philosophical tracks, not to mention the fact that it totally syncs up with The Wizard of Oz, have made it an almost sacred work of art for fans. That's right, Pink Floyd's The Dark Side of the Moon has become a cultural icon. In my opinion, for some reason. I just don't particularly like it. And its title is a part of our household lexicon. Incidentally, the title's release in 1973 came just months after the Apollo 17 mission, the last time to date that people walked on the moon, and arguably the peak so far of human space exploration. It just goes to show how little we still know about our closest celestial neighbor. Now, for decades, even centuries, the phrase "the dark side of the moon" has haunted our collective imagination with mystery. It's become a metaphor for the unknown and the insane. It evokes the image of a cold, untouched landscape hidden from human eyes where anything could be lurking. But what if the entire premise is wrong? What if there is no such thing as a dark side of the moon? And what if the truth is actually even more mysterious? The origins of the myth. The myth of the dark side of the moon is based on the simple fact that you can't see about 41% of the moon's surface, at least not here on Earth. That's because it is something called tidally locked. The technical definition of tidal locking reflects the fact that one lunar rotation, its day, so to speak, takes the exact same amount of time as one orbit around Earth does, 27 days. However, it's easier to think of it as not rotating at all. Presumably, the moon used to rotate just as the Earth does, but since the Earth is nearly 4 times the size of the moon and considerably denser, its gravity pulled on the moon enough to slow this rotation and eventually stop it. Now it's like a ball tied by string to the tetherball pole of the Earth. As the moon orbits around the Earth, the taut gravitational string keeps the same side facing the Earth at all times. The problem with the myth lies entirely with the word dark. The far side of the moon, as it should really be called, is not dark at all. In fact, it receives just as much light as the near side. During a full moon, the moon is on the opposite side of the Earth from the sun, so all the sun's light falls on the side that we can see. As the moon completes its orbit, more of that light falls on the far side, which we can't see, and less on the near side, creating the phases of the moon. During a new moon, the moon is on the same side of the Earth as the sun, so all of its light falls on the far side. The mystery behind the misnomer. Although the term dark side might be a misnomer, the mystery it invokes is somewhat accurate. Before 1959, no human being had laid eyes on the far side of the moon. It was terra incognita, a blank canvas onto which humanity projected its wildest dreams and also its most terrifying fears. By Galileo's time, the moon was understood to be a sphere in an orbital system with the Earth, and using a telescope, he was able to extensively map its features in his treatise Sidereus Nunicus. He also documented the phenomenon of libration, where the moon's orbital tilt combined with the Earth's spherical shape to allow us to see the edges of the far side of the moon. This is why, in total, 59% is visible. From this point on, astronomers were generally conservative with their speculation about the far side, guided by the scientific principle of mediocrity. This principle states that any given member of a category, be it a person or a planet, is more likely to be typical of the category than exceptional. In the case of the Earth and the Moon, this informs the belief that the two bodies are nothing special, similar to billions of others floating around the galaxy. As a result, most scientists before the 20th century would have told you that the far side of the moon was likely pretty similar to the near side, a whitish-grey surface. However, one German astronomer, Peter Andreas Hansen, had a much more interesting theory. Though it may seem fantastical, Hansen was actually a genius of astrophysics and was responsible for some of the most accurate calculations of the moon's motion at the time. Based entirely on gravitational mathematics, he postulated that the moon's center of gravity was actually around 53 kilometers or 33 miles closer to the Earth than its geographical center. That might not seem like a lot, but the gravitational imbalance could have resulted in the moon's primordial atmosphere and water being pulled to the far side. Hansen claims the far side could have oceans, air, and even life, all hidden from view. Of course, writers got even more imaginative. A prime example is Edmund Hamilton's 1929 short story, The Other Side of the Moon, in which a race of intelligent beings created a sealed subterranean refuge 500 miles beneath the surface of the lunar far side to survive as the moon's atmosphere slips off into space. In 1922, Johnny Gruelle, the creator of Raggedy Ann, wrote the illustrated The Magical Land of Noom. In the book, two children, Johnny and Janie, build a flying machine out of old boards and wooden spools that unexpectedly takes them into outer space and to the far side of the moon, where they encounter the enchanted kingdom inhabited by moon people. Naturally. However, as the Cold War heated up and the space age dawned, the far side of the moon turned from a place of mystery and imagination to something else entirely. A place to conquer. If the Nazis aren't already there. The first glimpse of hidden world. While Apollo 11 is often thought as the final victory in the space race, the USSR and the United States first raced to see the far side of the moon. In this case, the Soviets actually got the better of the Americans. On the 4th of October 1959, they launched Lunar 3, usually called Lunar 3 in English, their third unmanned probe aimed at exploring the moon. Lunar 1 was the first spacecraft to escape Earth's gravity, and Lunar 2 was the first to physically strike the moon. However, Lunar 3's goal of photographing the far side was so ambitious that Soviet officials did not even publicly reveal it beforehand. It was such an incredible feat that they didn't expect it to work. To take these pictures, the spacecraft itself had to be revolutionary. It was the first ever to be successfully stabilized along all three axes thanks to a sophisticated attitude control system that utilized gas jets to rotate and orient itself. For most of its flight, the probe was spin stabilized. In other words, it didn't wobble or rotate while following its trajectory. However, once it reached the far side of the moon, it had to orient itself to take photos. But it had to know when and how, using 1950s technology. First, a sensor detected the sun, alerting the attitude control system to align one axis in that direction. A photocell then detected the moon. Next, using its gas jets and highly controlled bursts, it corrected its orientation ever so slightly to aim its camera at the surface of the far side. Finally, it started taking photos. The cameras themselves were a major technological innovation as well, since space photography is considerably more difficult than photography on planet Earth. The entire system, called Yenisei 2, contained two lenses, one of 200mm focal length and the other of 500mm. The former was designed to capture the entirety of the far side surface in a single photo, while the latter could focus on specific regions. As Lunar 3 passed over the far side on the 7th of October 1959, the camera took 29 photos over 40 minutes, alternating between the two lenses. It was about 65,000 kilometers or 40,000 miles above the lunar surface. These photos required very special temperature and radiation-resistant isochrone film, which the Soviets had ironically obtained from a captured US spy balloon. The Cold War, everybody. Now, after the probe took its 29 photos, it faced arguably the biggest challenge of all, getting them back to Earth. At the time, returning a spacecraft to Earth without it burning up in the atmosphere was still something engineers were working on. The first spacecraft to achieve the goal wouldn't be until August 1960 with the American Discoverer 13 mission. Lunar 3, which was launched in 1959 though, wasn't capable of physically returning the film. Instead, it had to transmit the photos back to Earth, which was hardly any easier given the technology of the time. First, it had to develop them while flying through space. Then it had to scan them using something called a flying spot scanner. Basically, this device uses a cathode ray tube to shine a light through the photo. This light is captured by a photomultiplier, a light-sensitive vacuum tube that converts it into an electrical signal that can be transmitted via radio, sort of a bit like a fax machine. When Lunar 3 came back around the far side into signal range of the Soviet base, the operator manually instructed the probe to begin scanning and transmitting the photos. The process for one image took around 30 minutes, but the first few were pure static because the probe was still far away and the signal was too weak. The scientists continued trying, and finally, on October the 18th, the signal was strong enough to actually send the images. The probe successfully transmitted 17 photos, 6 of which were published, the first ever images of the dark side of the moon. First photos of the far side. Mysterious or monotonous? The images of the far side of the moon, though admittedly very low resolution, still stunned scientists with what they revealed. No, there weren't any magical kingdoms or alien bases, disappointing we know. But however, contrary to general expectations, it was geologically considerably different from the near side. The near side of the moon that we all recognize is dominated by Maria, the large dark plains that create the famous man in the moon face, covering about 31% of the near side surface. These seas are ancient lava flows from when the moon was geologically active that pooled in its many impact basins. Long since cooled and solidified, the rocks and dust of the Maria consist of far more iron than the surrounding highlands, making them appear a darker grey. In an ironic twist, the dark side of the moon is actually quite a bit lighter than the near side. It features hardly any dark grey Maria at all, covering less than 2%. The Soviets quickly named the largest mare the Sea of Moscow, breaking from the lunar naming convention specifying that Maria be named after weather and other abstract concepts, hence the Sea of Tranquility, the Sea of Clouds, etc. To keep the name, the Soviets successfully convinced the International Astronomical Union that Moscow is a state of mind. Instead of Maria, the far side of the moon is dominated by impact craters of all sizes. Many overlap, creating a brutal, rugged landscape pockmarked by celestial violence. This revelation was met with profound disappointment from the public. A journalist for Life magazine called it more monotonous than the known face. Many, perhaps secretly hoping for signs of life, ancient civilizations, or alien astronomical features, considered the homogeneous surface underwhelming. Yet for astronomers who, led by the principle of mediocrity, had long expected it to be similar to the near side, the images were surprising, exhilarating, and mysterious. Why were the two sides of the same celestial body so different? The depth of the mystery. The photos captured by Lunar 3, grainy though they were, ushered in an entire new chapter of lunar science. This is usually referred to as the lunar dichotomy, or sometimes the lunar far side highland problem. This reflects the fact that the far side is covered with cratered, mountainous terrain rather than the smooth Maria of the near side. Now, there has been further exploration of the far side. From 1966 to 1967, NASA's Lunar Orbiter program extensively mapped the terrain, and later Apollo 8, 10, and 17 made 24 Americans the only humans to ever witness the far side firsthand. Astronaut William Anders said, quote, "The backside looks like a sand pile my kids have played in for some time. It's all beat up. No definition, just lots of bumps and holes." A soft landing was not achieved until the China National Space Administration's Chang'e 4 mission in 2019. The robotic U-22 rover used lunar-penetrating radar to analyze the moon's inner structure. In 2024, Chang'e 6 then brought an actual sample back from the far side. Still, none of this exploration has been able to provide enough data to yield a definitive explanation as to why the two hemispheres are so different, though it has fleshed out in great detail just how different they are. First, the crust on the far side of the moon is far thicker than the near side, with an average difference of 15 to 20 kilometers, that's 6 to 9 miles. Presumably, this is the reason for the simple difference in appearance. The thinner crust on the near side meant that when the moon was geologically active, magma could more easily reach the surface, usually as a result of asteroid impacts. The impacts would break through the crust and lava would pour out, filling the impact crater and contributing to the Maria. On the far side, the thicker crust prevented asteroids from penetrating through to the magma. The impacts left large craters that were never filled in with lava. Nevertheless, this still begs the question of why the crust is thicker on the far side. Furthermore, the composition of the two hemispheres is dramatically different as well. The near side contains far more creep elements, potassium, rare earth elements, and phosphorus. Because these elements do not easily crystallize as a mantle cools, they remain in the last bits of molten material. Consequently, you'd expect them to be evenly distributed. The sample brought back by Chang'e 6 similarly revealed that the far side has much less water than the near side. Now, the near side isn't exactly a steamy swamp. Samples from the Apollo mission showed just around 200 parts per million of water. But the far side is a couple of orders of magnitude drier at just 1.5 parts per million. Now, although all the data gathered about the far side of the moon hasn't been enough to fully solve the mystery of the lunar dichotomy, it has been enough to develop some good theories. The more dramatic, albeit less likely theory is called the Big Splat. Adherents to this theory claim that at one point, Earth had two moons, and they collided together. This theory relies on the prevailing lunar formation theory, in which the early Earth and a Mars-sized body called Theia collided, creating a massive debris field that coalesced into the moon. However, the Big Splat theory holds that instead, two moons were formed. The second, smaller moon became trapped in a Lagrange point, creating a stable two-moon system for millions of years. Finally, though, the tidal forces destabilized the delicate gravitational forces, and the two bodies collided. Since they were essentially in the same orbit, the difference in relative velocity was minimal, so the collision was less violent than otherwise. The smaller moon basically splattered across the larger one like a pancake, creating a layer on one side that eventually became the crust of the far side of the moon as we know it. The big splat would also explain the geochemical differences as well. Basically, if the impact happens at the right time, when much of the moon's mantle had cooled but the creep elements remained in a small liquid layer, the force could have pushed them to the near side. Though intriguing, the big splat theory does face a major problem. While the compositions of the near and far side differ enough to be relevant at a scientific level, they're not that different. If you pasted one celestial body over another, you'd expect it to be a lot different. Just imagine taking Mars and spreading it like clay over one side of the Earth. The difference would be quite large, wouldn't it? Poor Australia. Another theory incorporates the idea of impact pushing chemicals to the near side without needing such a large celestial body. Namely, it blames the compositional differences of the hemispheres on the large asteroid impact that formed the South Pole Aitken Basin on the far side. At 2,500 kilometers in diameter or 1,600 miles, it's the largest impact crater on the moon and the second largest confirmed impact crater in the solar system after Utopia on Mars, as well as the largest impact crater is called Utopia? Why? As well as the landing site for both the Chang'e 4 and Chang'e 6 missions. Scientists believe that an impact of this size could have created enough heat to carry the creep elements to the near side. Similarly, it would account for the lack of water on the far side, either due to the physical force of the impact or by a vaporization of water in the mantle. However, this asteroid impact doesn't explain the difference in crust depth. If anything, the impact would have caused the opposite. Therefore, the current leading theory is that of the blazing furnace. Relative to the moon, the Earth is very geologically active, and in its early days, it was even more so. The young molten Earth reached blistering temperatures of 2,500 Celsius or 4,500 Fahrenheit, which would have roasted the moon. Since the moon quickly became tidally locked, only the near side was exposed to this inferno, while the far side faced the cold of deep space. With such a dichotomy of heating, you can understand why they now have such a dichotomy in appearance and composition. For one thing, the heat kept the near side molten for much longer. It would have been so hot that some of the molten elements, like aluminium and calcium, would have vaporized. The noxious atmosphere would have then floated to the far side, where it would have condensed into an otherworldly snow that fell down on the lunar surface, caking it in what would eventually form its thicker crust. The blazing furnace explains the difference in composition as well. Since the near side stayed molten longer, the creep elements, being the last to crystallize, ultimately migrated there. Water would similarly have remained with the last liquid magma, meaning most of it would have ended up on the near side. For some, the blazing furnace may seem a bit boring compared to the other options, but it is certainly the only theory that can explain all the information we have about the dark side of the moon. The far side of the moon is a new frontier. So China's Chang'e missions are just the beginning. Nations are racing to explore the dark side of the moon. It's partly to solve the long-standing cosmological mystery that surface dichotomy, but more importantly, it's prime scientific real estate. While the far side might not actually be dark, it is quiet. Because the moon itself acts as a shield, it's the only place near us that isn't bombarded by the relentless barrage of radio frequency interference that emanates from Earth in the form of radio and TV broadcasts, ever-increasing satellite communications, and of course billions of cell phones. This makes it the perfect place for a radio telescope, which could be used for a number of exciting pursuits. First, it would allow scientists to more easily study the 21-centimeter hydrogen line. From about 380,000 years after the Big Bang until the first stars ignited hundreds of millions of years later, the universe was dark and filled with hydrogen gas. Occasionally, it emitted a faint radio signal at a wavelength of 21 centimeters, which is 1,420 megahertz. However, as the universe has expanded, these radio signals have been stretched to ultra-long wavelengths over 10 meters, which is below 30 megahertz. As a result, they're blocked by the Earth's ionosphere and easily camouflaged by radio interference from satellites. By exploring the 21-centimeter hydrogen line, a radio telescope on the far side of the moon could provide new insights into the formation of the universe, cosmic inflation, and indeed the nature of dark matter. Planetary defense would also benefit from a far-side radio telescope as well. It could take more accurate measurements of near-Earth objects so as to better predict their trajectories and provide early warning of an impact. And finally, it would help astrobiologists. Many pre-biological molecules are detected along weak spectral lines, so the far side's radio silence would make them easier to pick out on exoplanets. Plus, the telescope could listen for the radio signatures of alien civilizations, which would likely be weak and possibly missed amongst all the radio frequency interference on Earth. With all this potential, spacefaring nations are racing to get a telescope on the far side of the moon. Perhaps the most ambitious is NASA's Lunar Crater Radio Telescope. For an estimated price tag of $2.6 billion, American scientists want to build a kilometer-wide telescope inside a yet-to-be-announced crater. Autonomous rovers would build the megaproject as early as the 2030s, which is quite an ambitious timeframe there, guys. To investigate the feasibility of the project, a team at NASA's JPL is currently building a 200-to-1 scale prototype to be tested in California. They now need to get approval for Phase 3 funding. Yet while the US remains in the planning stages, China is already on the move. Chang'e 6's successful return of samples from the far side was just the beginning of an ambitious plan to build a permanently inhabited moon base. Chang'e 7, with an expected launch date in 2026, will more extensively explore the lunar South Pole and find resources for a future base. Chang'e 8, planned for 2028, will test technologies like life support and 3D printing to prepare for human exploration. The first crewed mission is set for 2030. Finally, from 2031 to 2035, robots will construct the moon base, which will welcome its first scientists in 2036. Corruption of the pristine. Now, with all these government plans to explore and even colonize the far side of the moon, some scientists are concerned that what has long been a symbol for the unknown may soon become all too known. In March 2024, the International Academy of Astronautics held the Moon Farside Protection Symposium with the explicit goal of preserving its radio silence. Scientists involved with the symposium believed that the pristine environment could turn into a Wild West scenario as nations rush to explore and exploit the far side. Space stations, orbiters, landers, robotic rovers, and finally bases would all emit radio frequencies that would electromagnetically pollute the far side and negate its use for radio astronomy. Ultimately, the symposium hopes to achieve preservation through international diplomacy, treaties, and regulation. These could be made under the administration of bodies like the International Telecommunication Union or the UN Committee on the Peaceful Uses of Outer Space. The precedent does already exist as several regulations aim to protect any shielded zone on the moon, also known as an SNM. Any agreement would merely take this one step further. So next time a song from Dark Side of the Moon comes on the radio, try not to get hung up on the inaccurate album title. Instead, consider Earth's faithful companion, destined only to show us her face. Her far side is no longer unseen, but it does still remain a mystery and a symbol of just how little humanity knows about even its closest neighbor. Thank you for watching.